Okay, perfect. All right. So today we're going to finish with the isolated singularities. Right. So last time what I said is if we have let's put ourselves back in the setting we were, in which we have an analytic function with an isolated singularity. Right. So we have let f have an isolated singularity. In A. Right, so what I mean by this, I mean that f is analytic in an open set containing A, but not, right, or in a punctured open set around A, right? So like you can view this as there exists some delta bigger than 0 such that f is analytic in, right, all points, the annulus or the punctured disk, right, all points Z, such that Z minus A is between 0 and delta. Okay, this is what I mean by having an isolated singularity. And what we saw is if the right, so we saw that if the singularity was that there were removable singularities, right, that sort of didn't matter at all, and that there were poles. Right, so we talked about removable singularities. Right, these were ones where the function can just easily be extended to A, and we talked about poles. Right, poles being just when, the reason why f is singular at A is because f looks like a 1 over Z minus A to some power. Okay? And so now what we're going to do is do a characterization of all the possible isolated singularities that can happen. Okay? And so for this, let's look at two properties. Let's say property A. Right, so we did this a bit in, so let's fix, maybe let me fix here. Let's fix some alpha real, or, I mean, not fixed, but think of alpha as just a real. And let's say the property A is that the limit as Z goes to A, right, of Z minus A to the alpha FZ is 0. And property B, right, of course, this is a property for a given alpha. Right, property B is that the limit Z goes to A of Z minus A to alpha FZ is infinity. Okay. Okay, basically, I should put absolute values. Right, so in particular, if this holds for alpha equals 1, basically means that it's a removable singularity. Right, and if this holds for alpha bigger, then essentially means it's a pole, right? Or the other way, if this holds for alpha equals 0, meaning the limit of fz of the norm goes to infinity, then what we did was we looked at, right, 1 over f, and we saw the order of the 0 of that, and we saw that this corresponded to the order of the pole. Okay? And now the picture to have in mind, let me just do it again. Right, I did this last time, is, there'll be, if we think of the real line and the values alpha, and for which values alpha this will be satisfied, right, A or B, then if for a certain alpha, let's say here, for a certain alpha, the property A is satisfied, let's say A is satisfied here, then for sure, if I make alpha bigger, right, this just goes to 0 faster, and so A will be satisfied in some region, right? For B is exactly the opposite, right? If B is satisfied at some point, then if I make it smaller, right, if I make this power smaller or more negative, then for sure this still is infinity because, right, I'm just dividing by bigger powers of Z minus A. And so the property B will be satisfied in a certain, right, in a certain region. Okay, so given a function f, we're interested in understanding these regions, the place for this right, the reals, for which this power or this limit goes to 0, and for which this limit goes to infinity. Right? These regions might be empty. Something might exist in the middle. Something might not. For sure, they don't intersect, right? Because it can't be that the limit is both 0 and infinity. So at least we know they don't intersect, but we don't know much more about them, right? And we know that they look, I mean, we know that they must look like intervals in this sense, but we don't even know if they exist. Okay, and so what we're going to do is sort of a trichotomy of what can happen for a function. So again, let's have f be isolated singularity in A. Let's say for to keep things interesting, f is not identically 0. Because when f is identically 0, things are not terribly interesting. Okay, so f is not identically 0 because we know that that's a very special property. Okay, let's suppose that there exists, right? Let's say that there exists alpha, right, real, such that A is satisfied. Okay, so there is some alpha for which that's satisfied. Okay, if that's the case, then the function, right, let's say g of z, right, equals to z minus a alpha fz, right? This function has a removable singularity. Removable. Right? Because I know that the limit of this function that goes to a is 0. So in particular, right, let's just recall this. In particular, the limit as z goes to a of z minus a times g of z is 0. Right? Because the limit of g of z is 0. If I multiply by z minus a, it can only be sort of, right? It's only going to 0 faster. Okay. Okay, so it's a removable singularity. Moreover, right, now if I take it, right, if I take the extension of the function, right, I put the value there equal to the limit, then actually g of a is 0. Right? Right, it's a removable singularity, and the extension there is for sure 0, right, because that's what the limit is. Okay, and so a is a 0 of g, say, of order right, of order k. Okay, let's say for some k. Right, the point being that this is true for some integer k. Okay, for some integer k. But now, if this is true for some integer k, right, then this means, right, that for all beta bigger than k, right, the limit as z goes to infinity of z, or z goes to a, sorry, of z minus a, right, to the minus k, minus beta, sorry. I have this good, well, yeah, let me do this way instead. Beta yeah, okay, let me maybe, because I'm writing too many, and then I need to define yet another parameter, so let me do this in another way, just so that I don't have to define as many letters. Okay, for all beta bigger than alpha minus k, I claim that the limit as z goes to a of z minus a beta, right, fz, goes to 0. Okay, why? Okay, because, right, so let's take this limit. Right, this is equal to the limit z minus a, right, of now z minus a beta minus alpha, right? And then z minus a alpha fz, so this is gz, right? But we know that, right, so z minus, we know that this number is bigger or equal than minus k, and because g has a 0 of order k, right, then if I'm multiplying by something that doesn't remove completely the 0, right, it's bigger than minus k, so it's not more negative than minus k, then the limit of this needs to be 0. Right? You should think, you should think of g of z as something like z minus a to the k locally, right? And so since I'm multiplying by something that doesn't completely cancel out this term, then this limit is equal to 0. Okay, we saw the proof of all this stuff last week. Okay, so what this means, right? Also, because on the other hand, it's also not so hard to see that, right? Because g of z is analytic and has a 0 of order k, sort of the complete opposite is true in the sense that, or I shouldn't call it the opposite, but the same thing happens on the other side, that for all, right, for all beta, or let's say, let me come up with another letter, for all tau smaller than alpha minus k, right, then the limit, right, of z goes to a of z minus a to the beta, right, fz is minus a to the beta fz is infinity, right? Exactly for the same reason, right? This limit is equal to the limit of z minus a to the beta minus alpha, or no, tau, sorry, to the tau minus alpha, right? And now if the thing I'm multiplying by is smaller or equal than minus k, or smaller than minus k, which is what I'm asking, then since this has a 0 of order k, I must get something going to infinity. Okay. So now there's something, right? There's something that I forgot to say, and it's an important point. I don't know if anyone noticed, which is that, in order for this function to be right, to be nicely defined all around the singularity, I actually need to pick a to be an integer, right? So alpha actually needs to be an integer. But if this is satisfied for any alpha, right? If it exists alpha such that this is satisfied, then it also must exist, right? Then this means that there's also an alpha integer for which a is satisfied. Okay. Why? Because if it's satisfied, right? If it's satisfied for a number, it's satisfied for all the bigger numbers. So I just take an integer, right? I just take something that's an integer that's bigger than the number I have that it satisfies. Okay? So if a is satisfied for any number, you just pick an integer slightly bigger than it. Because it's satisfied by an integer, right? This function then is right, is nice and analytic, right? Otherwise, if this is not an integer, we would have issues defining this, right? And as a removable singularity, and because of the theory that we had for zeros, for order of zeros, we get that, right? It must be that if beta is bigger than alpha minus k, then this limit is 0. If tau is smaller than alpha minus k, then the limit must be infinity. So in particular, we get that, right? We get a proposition, right? So what did we show? Let me write it out, right? That if a is satisfied for any alpha real, then there must exist an integer. Okay, let me call it m. Okay. Let me see if there's any special letter that is usually used. Sometimes, yeah, people usually use h, so let me use h. So there's h an integer, right? Which here h is being alpha minus k, right? Okay, there is an integer such that a is satisfied for all alpha bigger than h, and b is satisfied for all beta smaller than h. Okay? And crucially, h is an integer, right? You should think of h as the degree, right? Given a function with an isolated singularity, h is sort of its degree, right? And it's and it could be the order of the zero or the order of the pole, depending if it's positive or if it's negative, right? So if h, okay, I need to look at it to see which one is which, right? So if you need to put a positive thing here to make the limit go zero, then you have a pole. If with a negative you still might see zero, or you need a negative to go to infinity, then you have a zero. And so h tells you about the order of poles or zeros, depending if some function has a zero or a pole. Okay, so now, before I erase, let me just say that this is actually, right, so this picture, that, right, the important picture being that, right, the important picture being that there exists, let me see how I can do this without destroying the theorem, right? So this property, right, that there exists some h integer such that a is satisfied for all alpha bigger than h, and b is satisfied for all b smaller than h, right? That the function has over degree of the singularity. What we showed here is that as long as a is satisfied for any point, then the picture is actually quite simple. These things meet, they don't intersect, right? There's still a value h for which we don't know what happens, but right, they come out of the same point, and this one goes to the right, this one goes to the left. Okay? Now, it's also not so hard to see that the same thing holds as long as b is satisfied for any alpha. Right? So I'll just briefly just mention this. Okay, but let me say here. Okay, so right, it's not so hard to see that if there exists some alpha such that b is satisfied, right, then the exact same construction holds, right? Then the same idea gives. Right, and here you can take two approaches. You can either just look at, right, if b is satisfied, then you construct a function that has a pole of a certain order. Or you can just look at 1 over fz and construct a function that has a zero of any order. I mean, that's how we understood poles to start with. So the exact same idea gives the exact same phenomenon, right? That there exists h in z such that, right, there's h here, and a gets satisfied in this side of this, and b gets satisfied here. Right, so exactly this picture. And so because of this, we have a theorem, and this is a very important theorem, that says the following. Okay. Let me put this h up there so that it doesn't bother me. Okay, so we get a theorem. Again, the same, let f have an isolated singularity at A. And then one of the following must hold. Right, so we have a trichotomy of things that can hold, like a classification theorem. Okay, so option number one, f is identically 0. This is the boring one. Right, this is boring. Okay, option number two, there exists, right? One of these things is satisfied for some alpha, and so there exists h integer such that right, a is satisfied for all alpha bigger than h, and b is satisfied for all alpha smaller than h. Okay, but now a third thing might happen. I'll erase everything. Okay, okay, so what might happen, right? We saw that if f is not identically 0, and either one of these is satisfied for either alpha, for any alpha, then we must be in world number 2. So the only option for world number 3 is that f is not identically 0, and none of these happen. So both neither, I should write this, neither A or B are satisfied. For any. Okay, so we might be in this very strange world where there isn't any alpha for which either B or A are satisfied. Right? This is a very bizarre function for sure. Right? It doesn't have limits in sort of a very, very strong sense. And so this is called an essential singularity. Right? And these are the problems. Okay, so world number 1, f is identically 0, right? Not very interesting. World number 2, basically it's a pole, right? Or either it's a removable singularity or it's a pole. World number 3, this very bizarre phenomena that we call essential singularity, in which neither A or B gets satisfied for any alpha, right? So the function is so nasty that I cannot make it go to 0 by hitting any amount of z minus a to any power, and I cannot make it go to infinity by hitting any amount of z minus a to some negative power, right? So this is a bizarre object that goes to both to 0 and to infinity so fast that I cannot kill it with any polynomial, one way or the other, right? Prevent it to go from 0 or prevent it to go to infinity. Okay, this is a nasty, nasty object. Okay, so now let's prove some interesting things about essential singularities. Maybe I'll leave this in the board. It might be useful. Okay, so let's see if we can understand some things about these nasty objects. So, okay, so definition, like FA is, or I say an isolated singularity A of F is an essential singularity if and only if neither A nor B is satisfied. For any alpha real. Okay, so now there's a very nice theorem. Well, I mean, nice in the sense that you can say something very nice, but it also shows how complicated these objects are. Okay, so here's a theorem. This, I believe, is due to Weierstrass. Okay. Right, so an analytic function comes arbitrarily close to any point in C in the neighborhood of an essential singularity. Okay, I mean, another way to write this, right, equivalently, if you prefer it in math terms, right, for all, like, let A, if A is an essential singularity of F, then for all epsilon bigger than 0, sufficiently small just to make sure that Fn is analytic in that I'm going to make a ball around A. I just want to make sure that it's analytic around epsilon. So let me say sufficiently small, right? So that I make sure that it's analytic in epsilon. For every epsilon sufficiently small, the image, right? So the image f of z for z inside the ball of center A and radius epsilon is dense in C, right? Or I can say, right, I can put the set of f of z for z in the ball, this set is dense in C. Right, so not only this function around the essential singularity goes crazy in the sense that it's going to 0 and to infinity, like at uncontrollable speeds, but actually gets arbitrarily close to any point in C. Right, so if I have an essential singularity, right, I mean, think about how complicated this object looks like. Right, if I have an essential singularity around A, and for any circle around F, if I apply F to this, I get essentially something that's dense in C. Okay, so arbitrarily close to any region, you get the whole, the essentially all of C or dense in C. Right. The proof of this now is actually quite easy. Right. Now the proof actually comes to us quite easily. Okay. So let's go by contradiction. Right. So we go by contradiction. let's say that this wasn't true and you weren't dense, the image wasn't dense, then there must exist A in C such that you don't come arbitrarily close to it. So there must also exist some delta bigger than 0 such that for all Z, right, in a neighborhood, f of Z minus, right, all Z, let me just say, for all Z in the neighborhood around A, let me write it like this, just because I don't want to keep track of the other epsilon, because it really is not needed. Okay, Z, f of Z minus A needs to be bigger than delta. Okay? So in other words, there must exist a in C such that f of Z minus A is bigger than delta in a neighborhood. Neighborhood of A. Okay, so we must have that this is bigger than delta. But so if this is bigger than delta, it means, for example, right, that the limit we have immediately, right, if this is always bigger than delta, then the limit of, say, Z minus A to the minus 1, for example, right, fz minus A, see with right, if this thing is always bigger than delta, then when I take the limit of Z going to A of this object, right, Z minus A to the minus 1 times f of Z minus A, this is always bigger or equal than Z minus A to the minus 1 times delta, right? So it's always bigger or equal than delta over Z to the minus A, so this needs to be infinity, right? Essentially what I'm saying is because the function fz minus A is bounded away from 0, f A is not an essential singularity of the function fx minus A, fz minus A, sorry. Oh. Right? We said that essential singularities needed to have this nasty thing that they go to 0 and to infinity very quickly. But if A is not, if nothing comes close to A, then the function fz minus A cannot have that. Right? Fz minus A cannot go to 0. And so, right? And so in particular, this limit needs to be infinity. And so A is not an essential singularity of fz minus A. Right? But if A is not an essential singularity of fz minus A, then it must be that there exists some beta, right, such that the limit when Z goes to A of Z minus A beta fz minus A goes to 0. Right? Because it's not an essential singularity, so equation A must be satisfied, right? Because there must be an integer such that equation A is satisfied. Okay? So, and in fact, if it's satisfied for some number, it needs to be satisfied for all numbers bigger. So we can actually pick beta to be positive because, right, if this limit is 0, then I can just have beta be, I can just pick a bigger beta, right? So I can pick, right? So we can pick beta bigger than 0, or say alpha bigger than 0, right? Because all we need is that alpha is bigger than this beta, right? And then we have that the limit Z goes to A of Z minus A alpha fz minus big A needs to be 0, right? But if this is the case, right, now I can just use triangle inequality because the limit of Z minus A to alpha times A, because A is fixed, is for sure, right, is for sure going to 0. Okay, so let me write that a bit more carefully. So the limit Z goes to A. Okay, I'll just start writing limit, but all the limits are Z goes to A. Z minus A alpha fz minus A right? Or maybe instead of the limit, let me just write the triangle inequality this way, right? This needs to be bigger or equal than z minus a alpha f of z plus minus, sorry, right? Just triangle inequality. Right, this is just triangle inequality, right? This plus this needs to be bigger or equal than this, right? So this is, I often write like this, triangle inequality, right? And so in particular, the limit, right? And the limit as z goes to a of z minus a to the alpha a goes to 0, right? Because alpha is positive and a is just a constant, so for sure this is the limit, right? And so the limit of this goes to 0, the limit of this goes to 0, so, right, the limit of this needs to go to something in absolute value smaller than 0, smaller or equal, so it needs to be 0, right? So the limit of z going to a, right? This limit goes to 0, this limit goes to 0 by hypothesis, so this one needs to go to 0 too. Z minus a alpha f of z goes to 0, right? And so, right, and so option A is satisfied for some alpha, and so it's not a, and so A is not an essential singularity. Singularity of f. Right, so this would be the contradiction. Okay, so now we know that around the region, right, then you will see essentially every point in C, or at least be dense in C. Okay, and so in the homework there'll be some examples of essential singularities. Right, you should think of, say, like exponential of, say, of negative powers of z, things of this type, and you'll see some examples in the homework. Okay, so now that we have sort of an understanding of this, the classification of the different isolated singularities, then let's go into something a little bit different. So let me erase it. Right, so of course, I mean, you could have functions that have singularities that are not isolated, and then there's a whole other thing. But for functions that just have singularities at isolated points, then we know that they must either not be real singularities, right, or they must be poles, and then the function is meromorphic, or they have this nasty behavior of being essential singularities that sort of are also, right, we also understand a bit about them. At least we know that what their neighborhood looks like and so on. Okay, so now we're going to talk about, today, what I want to do for the rest of today, and then maybe on Friday I'll prove at least a version of the general Cauchy's theorem, is to think about function f as a mapping. So functions are, like, analytic functions are quite special. They're not just, as we've seen many, many examples of this. But before we get there, I just want to show an example of how, right, or maybe I should say, what's going to happen in maybe the next 3 lectures is you're going to see a lot about the balance between analytic functions and complex analysis, and understanding geometry and topology and so on of the set in which they're defined, right, via whether Cauchy's theorem works or not, and so on. We already saw winding numbers and things of this type. And also, another thing you can do is understand the set of zeros of a function, right, by properties of the analytic function itself, right? I mean, the winding number wasn't quite an example of this yet, but it's definitely going in that direction. And so what we're going to do, I mean, I now have 2 minutes, so there's no point in starting, right, is we're going to do a formula involving an integral that's going to count the zeros of an analytic function in a region, okay, via, very much analytic winding numbers type things. And then we're going to understand that analytic functions actually are mapping in the sense that they map open sets to open sets. Right, so think about this for a bit, right? When we have a continuous function, we know that the inverse image of an open set is an open set, but it's not at all true that open sets go to open sets, right? Think of, for example, the sine over the reals, right? Over the reals, if you take sine of x and you take a big open set in the reals, the image is just a closed set from -1 to 1. Right? And so, but in complex analysis, this won't be the case. And we saw already some versions of this type of thing. And so we'll see that, and this will give us access to something called the maximum principle, which is extremely useful to prove many, many things and do lots and lots of exercises. Okay, so I'll see you in 15 minutes or so. There's no point in starting because I wouldn't have time to do anything, and I'll do this on the second part of the lecture. All right, thank you.